So in this next example, we are going to consider arc length of a parametric curve. So let's say that this is a parametric curve given by x of t, y of t, and what we're going to do is we're going to partition the time interval up into pieces, and by doing that, we're going to create these points on the curve. And then we know how to find the distance between straight lines in the plane. We can just use the distance formula to do that. So we can approximate the arc length, the curve length here, with the sum of the lengths of these segments using the distance formula, or if you want, Pythagorean theorem. So for example, let's say we bring this portion of the curve over here. And that looks like this. Then we could drop a perpendicular here. And you've got the curved portion here. So that is ds. That's our little piece of arc length. And this is our dy, which is our increment in y. And this is our dx increment in x. So then by Pythagorean theorem, ds is going to be square root of dx squared plus dy squared. So ds actually is going to be the length of the third side of the triangle, which is approximating the arc length, and in the limit they're actually equal. And then I'm going to take dx squared, multiply it by dt squared over dt squared, and the same with the dy squared, multiply by dt squared over dt squared. So then notice that dt squared is a common factor, so I factored that out on the right, and then the square root of dt squared is dt. Then we've got dx dt squared here, and dy dt squared here. And then dx squared over dt squared is dx dt squared, dy squared over dt squared is dy dt squared. So these are the x and y derivatives squared times dt. So that's our arc length element. So then the arc length from time alpha to time beta is going to be the integral from alpha to beta. We're going to add up all these little pieces ds. Okay, so we're really doing the integral of ds. Little pieces of arc length, and then the integral adds them up. So well, let's put this formula to work here. So let's say we want to find the arc length of the asteroid, x equals cosine cubed and y equals sine cubed. T goes from 0 to 2 pi. So we got to be a little bit careful here. Because orientation matters with these parametric curves, and actually we have some symmetry here. We can find the arc length in the first quadrant and then multiply by 4. Let's first find out what time points are the corners. So if t is equal to 0 where we start, we get cosine cubed of 0, which is 1, and sine cubed of 0, which is 0. So that's this point right here. So that's t equals 0. T equals pi over 2, we get cosine of pi over 2, which is 1, cubed is, cosine pi over 2 is 0, cubed is 0, sine pi over 2 is 1, cubed is 1. So this up here is going to be at time pi over 2. And then if we keep going around the edge, this is at time pi. And then 3 pi over 2. And then this would be back to 2 pi. So let's first figure out our ds here. So ds is the square root of dx dt squared plus dy dt squared. So x is cosine cubed t. So the derivative of that is going to be 3 cosine squared t, and then times the derivative of the inside, which would be negative sine t, and then plus, and that guy gets squared, and then plus dy dt cubed. So this is, again, function to a power, so the 3 comes down in front, decrease your exponent by 1, so sine squared t, times the derivative of the inside, cosine t, and that guy gets squared. So let's see, this is going to be, we will square the negative, we get a positive, square the 3, we get 9. Cosine squared squared, so cosine to the 4th t, and then square the sine squared t, and then in the other piece square the 3, we get 9, square the sine squared, sine to the 4th of t, and square the cosine squared t. So we hope we get a perfect square here. So let's factor out a common factor. So we've got a common 9. And then we've got 4 cosines here and 2 cosines here, so we can take out a cosine squared t. We've got 2 sines here and 4 there, so we can take out 2 sine squareds. Or sorry, 2 sines. Take out a sine squared. So if we take 9 cosine squared sine squared, what's left here is cosine squared t. Plus, take out the 9, 2 of the sines, 2 of the cosines, we're left with sine squared t. And that works out real nice because this is just 1. So we're taking the square root of 9, which is 3, square root of cosine squared, which is cosine t, and square root of sine squared, which is sine t. So that worked out nicely. So now our arc length here, let's do the integral from 0 to pi over 2. So that's going to be 1/4 of the arc length, and then we'll multiply by 4. And then we are integrating 3 sine t cosine t dt. So the 3 can come outside here with the 4. That gives us a 12 outside. And let u equal sine t, then du is going to be cosine t dt. So this will be integral. And then let's see, we want to plug 0 in for t here. Sine of 0 is 0. Plug pi over 2 in for t. Sine pi over 2 is 1. And then this will be u du. So that's going to be 12 times, this will be u squared over 2 is our antiderivative. And that's going to go from 0 to 1. Plug in 1, we get 1/2 minus 0. This is 12 times 1/2, which is 6. So that means that each one of these pieces is 1.5 in length. Now, notice here, counterclockwise is our increasing t here. Note that if you were to do the integral from 0 to 2 pi of the same thing, 3 sine t cosine t, so if you did not use symmetry, you would actually get 0. And the reason is because in these first two pieces, when you integrate, you're going in decreasing x direction. Second piece is you're going in increasing x direction. So these first two pieces is counting as positive length and the second two as negative length. So you got to be a little bit careful here. You're getting canceling lengths. So you don't want to do that. That's because of the orientation of the curve. So canceling length. So the moral of the story is that if you have symmetry, you should use it. And if you get 0 for an answer for length or for area, then you had some canceling go on inside there. If you get a negative answer for length, then you just want to change the sign to a positive. So it just depends on how things are oriented.